Hello class. Let's review some reactions that we've seen so far. So what if I have an ester and I treat it with sodium hydroxide and then do a acidic workup? What's that going to give us? That's going to take us from an ester to a carboxylic acid, right? And that reaction right there is called the saponification. Remember that one? Now we can also, here's the new reaction that we're going to go over today, or right now I mean, we can take a ester and we can treat it with acidic conditions. And that right there is going to give us our carboxylic acid. And this reaction is called the hydrolysis, or we could say, word it this way, ester hydrolysis. Now that reaction right there may be looking a little familiar, possibly because do you remember, let's see here. Remember this one? Where you take a carboxylic acid, treat it with an alcohol under acidic conditions, and what are you going to get? An ester. Remember what that reaction name was? That's the Fischer esterification. But take a look at that pink reaction in the middle and the green one on the bottom. Ester hydrolysis is exactly the reverse of Fischer esterification. So if you know the mechanism for Fischer esterification, just doing the mechanism in reverse is going to get you with the ester hydrolysis mechanism. So I would like to take the time to show you that mechanism, this one right here in the middle. But please note that this mechanism right here is simply the reverse of the Fischer esterification. So here we have the overall transformation. So let's take the hydronium and expand it out. Okay, so let's expand it out here. So what would the first step be? Well, we're going to do a protonation step. So that all these mechanistic steps are going to be reversible. So we will have an OH there. That's going to make that positive OR like that. And will give us some water. Okay, so what did that do? That activated that carbonyl carbon. So we could have a water molecule now come in and attack. So that will give us this. And then the water came in and attacked. So that's going to be positively charged because that water molecule is right there. And that oxygen has 3 bonds. So now what's the next step here? We're going to do another proton transfer step because we have excess amount of water present. And so another water molecule is going to come in and abstract that proton. So there we have that, plus what? We just regenerated the hydronium. Now when I look at the overall reaction, I see that the OR piece has to leave. So can I bring down some lone pairs and kick it off? If I did that, then I'd generate a negative species. I'm under acidic conditions, so I can't do that. So we have to turn the OR into a good leaving group. And so that's going to give us that species now. And we just generated some more water. So now we can see a lone pair coming down and kicking that guy off. So now we are what? We have an OH, a double bond OH, plus the ROH. So now we have our alcohol. So are we there yet? No. We have one more proton transfer step left that we need to do. And I'm going to expand out this hydrogen so we can see how that occurs. So we have water present right here. That's going to come grab that like so. To give us our product. So we just made ourselves a carboxylic acid. So the next reaction that we want to look at is when we take a ester and treat it with a amine, and then we will get an amide as our product, and we call that reaction amino analysis. So we're going to take a look at that when I clean this board. Amino analysis is when you take a ester and you treat it with a ammonia, a primary amine or a secondary amine, and you generate the amide. That's amino analysis. That's the overall transformation. At equilibrium, the amide is favored because amides are lower in energy and more stable than esters. But the process is very, very slow. So this reaction right here is not very practical. It just does not react fast enough for our purposes. So we have a faster way and a more efficient way to make amides, and we've already seen that reaction. And that is when you treat it with acid chlorides. That would get us an amide at a more efficient rate and is just more practical. So you won't, amino analysis with esters, you typically won't see that, but it is there, and I want you to be aware of it, but also know that it's more practical to use an acid chloride to make your amides. But we can also take a ester and treat it with a reducing agent and reduce it into an alcohol. So if we use lithium aluminum hydride in step 1, and then step 2 we're going to do an aqueous workup. we can generate an alcohol like that and totally reduce it. But we need to have at least 2 equivalents of the lithium aluminum hydride in order for this reaction to work. Now, another thing to note is the molecule right here, the whole molecule right there, is from that piece right there. But we also generate a second alcohol. And that second alcohol is going to be this guy. So where did this alcohol come from? Came from right there. So whenever you reduce esters, you're going to generate 2 alcohols. Now the mechanism of this is analogous to when you took a acid chloride and treated it with lithium aluminum hydride. It's very, very similar. But we have an ester, so let's look at that mechanism. So what do we have? Lithium aluminum hydride. It's going to have our 4 hydrogens on there. It's going to be negatively charged. What's going to happen? Well, go like this. So that's going to give us OR prime. And then we've added our hydrogen like so. Okay. And then we'll pair the tetrahedral intermediate. It's going to collapse back down to knock off the OR. So what do we have? We have the aldehyde intermediate. And that is why you need that second aluminum. So I'm going to draw it like this. That's why you need at least 2 equivalents of the lithium aluminum hydride so you can do the second reduction. Just added another hydrogen. And that is, so what are we going to do next? Well, that's step 2, where you add a little bit of acid or some aqueous workup, okay, to do the protonation. So let's just say if I do a little acidic workup, have this guy come down to give us our product. OH. But when this guy left, the OR prime, what do we have here? OR prime negatively charged. This will also see the acid from the second step. So we're going to have another protonation event to give us our second alcohol. So what I would recommend doing is look at this mechanism and compare it to the reduction of acid chlorides with lithium aluminum hydride. And you'll see how the mechanism is very, very similar. So if I want to make some comparisons now. Okay, so I want to keep this mechanism up here in the middle. So do you remember with acid chlorides, and we did, let's say we treat it with the lithium aluminum hydride. The first intermediate that you're going to get is the aldehyde, just like this one, this aldehyde right there. And then you do the second equivalent and then the acidic workup to give us our alcohol, right? Remember that? Okay. What reagent would I use if I wanted to take an acid chloride and reduce it to the aldehyde? Do you remember what that reagent's called? It's a mouthful for sure. So what it was called, if you did not use that one, you would use lithium lithium tritert butoxy, lithium tritert butoxy aluminum hydride. That was the reagent that would stop at the aldehyde. Now contrast that. What if, just like with esters now, what if you wanted to take your ester and stop it at the aldehyde? What reagent do you use? And with esters, you typically don't use lithium tritert butoxy aluminum hydride. You use something called dibal. Or, well, let's see here. Different texts call it different things. DIBAH. If you use that reagent, you're going to stop at the aldehyde. Now, what does dibah look like? And then we will spell out its name. And if we draw it out, we can figure out the name of this compound here. Okay. So here's our species. Now let's look at it. D stands for the di. Isobutylpropyl. Diisobutyl. Now I'm messing it up here. Diisobutylpropyl aluminum hydride. Oh, I totally slaughtered that name. That group right there is called an isobutyl. Where did that propyl part? That's no good. Diisobutyl aluminum hydride. Okay. So that reducing agent, diba, is going to stop, will reduce an ester to its aldehyde. So it's kind of, this reagent is kind of analogous to this mouthful down here in pink. Okay. Next, we are going to look at Grignard reagents reacting with esters and figuring out what that makes. Now let's take a look at a reaction where you can take an ester and treat it with a Grignard reagent. We could use any Grignard reagent. Let's use a simple one. And the Grignard reagent has to be in excess or at least 2 equivalents. We'll just say excess. And after the first reaction, then you once again have to do a aqueous or acidic workup to protonate the oxygen atom. When you do that, what are we going to generate? Now this is analogous to taking a Grignard and reacting it with the acyl chlorides. What did we get? We would have added the 2 methyl groups. So the methyl groups right there are those right there. And you see that I added it twice. So what do we make? We make a tertiary alcohol. So the mechanism is very, very similar, in which if we draw out our Grignard like this, or we could, so we don't confuse ourselves, it's actually bonded to the carbon and you have the 3 hydrogens right there. This bond is going to come in and react in that manner. And let's go down this way. So that's going to give us I'm thinking this green pen is almost near the end of its life here. And then there's that. So what would the next step be? We'd bring these lone pairs down to kick off the OR group. And there we have our ketone plus the OR minus. Okay. Now we'll just do it again. We will take another Grignard. And that's going to come in and react with the ketone. And now we will do the second step, which is adding a proton. So we would have a proton transfer step to give us to our product right here. So very similar and should be a familiar mechanism for you. Okay, what are we going to talk about next? Let's see here. So let's just mention, how do you prepare amides? And we've looked at a lot of reactions in this chapter. We can make amides from acid chlorides, acid anhydrides. We could even use esters. But remember what I said about esters. Esters are just too slow. So what are the best ways to prepare amides? It would be to use acid chlorides or acid anhydrides are typically the best way to make amides. But remember, when you use, well, just go back when you want to look at how to make amides with these two reagents. Just double check all the rules with those, okay? What I want to talk about next is taking a look at some of the reactions of amides. So we've discussed in depth how to prepare amides, but now let's take an amide and do something with it. That's what we're going to look at next. So the first reaction that we want to look at is the acid-catalyzed hydrolysis of amides. So when you take an amide and treat it with an aqueous acid, you can generate a carboxylic acid. Now this reaction is typically slow, and so to help get this reaction going, we're going to add some heat. So in order to do acid-catalyzed reactions of amides into carboxylic acids, you have to add a little bit of heat. Now, when you add that little bit of heat, the reaction goes, and what do we generate here? We generate an ammonium. And when we look at that, expand out that ammonium, we see that it has 4 bonds. Okay? And its pKa is approximately 9. Let's double check that real quick. Okay. 9.2. And on this side of the equation, hydronium's pKa is about negative 1.7. So that's a drastically large difference. And so equilibrium is like favored to the right immensely. And so this reaction is essentially irreversible. Like once you get it going, it's just going to go until you get to the product. And you can't take the carboxylic acid and the ammonium and go backwards. It just does not work. So if we take a look at the mechanism of how this is happening, I hope that you find that these mechanisms there's a lot of similarities. So we have our hydronium right here. Let's write it out like that. So what do you think the first step's going to be? Well, we're going to do a protonation step. So when we do that protonation step, what are we going to get here? There's our amide. So that's positively charged. And then we generated some water. Now, what have we done? We've now activated the carbonyl so the water can come in and attack. And then we have that group right there. Then we're going to do another proton transfer step. We're going to have enough water to go around. Plenty, plenty. Okay, and then what did we also regenerate? We regenerated the hydronium. Now what do you think? Is an amine a good leaving group? If it left, what would it leave as? A negative charge. And we're under acidic conditions, so we can't do that. So we need to protonate that nitrogen atom. So we added a hydrogen, so that makes that a positively charged nitrogen. Now it's a good leaving group. So what can we do? We can now make it leave. But what did we also generate? We generated some more water. Not that one. So now we have OH there. Have we gotten to the carboxylic acid yet? Not quite. So at this point, what do we have also? We have the NH3 that just got knocked off. So the NH3 can, in fact, act as the base to give us our product. Plus our ammonium. So you can see that this guy right there and there are the same. That is our product, and that is the mechanism. Amides can also be hydrolyzed under basic conditions. So that's the reaction that we're going to look at next. This one was acidic conditions. Now we will look at basic conditions. So hydrolysis of amides under basic conditions is even slower than acidic conditions. Now why is that the case? Because under acidic conditions you protonate this oxygen, which activates that carbonyl carbon. Under basic conditions, that carbonyl is not as active or activated. So what happens is the sodium hydroxide right here, it's just going to attack directly. So now we're going to generate something that looks like that. And now you can see that we're under basic conditions. So this lone pair can collapse back down and kick off onto the amine. So now we have carboxylic acid plus NH2 minus like that. Now what's interesting about this next step is the fact that now you have a carboxylic acid and you have this base, and it's really, really strong. You can't stop it from reacting. So if I extend this hydrogen out, you're basically saying, hey, this reaction is going to go to completion because we are going to now come in and abstract that proton. It's simple acid-base chemistry. And then we would get ammonia. And now what are we going to have to do? We're now going to have to do step 2, which is just the acidic workup. And why do we need that? Because we have a carboxylate right here. So that carboxylate needs to be protonated. And when you do that, you will generate our carboxylic acid. Just like that. You can also reduce amides into primary amines. It's very analogous to when you take an ester and you reduce it into an alcohol, or a acid chloride and reduce it into an alcohol. Very, very similar. So let's take a look at that next. Okay, the next reaction is the reduction of amides with lithium aluminum hydride, and we have that in excess. So here's our amide. First step, lithium aluminum hydride. You see that will reduce us to a primary amine. So what's happening? We are getting rid of that oxygen atom completely, just falling off. So this mechanism is slightly different than what you've seen in when you compare treating a acid chloride with lithium aluminum hydride. There is some differences here that I want to highlight. And then after you do that first reaction, you have to do an aqueous workup. Okay, so let's take a look at the mechanism and how this is all going to go down. Okay. Let me take a look at one other thing before we jump into that. Okay. Let's take a look at the mechanism here. What we're going to do is we're going to take the lithium aluminum hydride right here. So let me double check on one thing before we get going on this mechanism. I just thought of something. Okay, so let's take a look at this mechanism here. So we have our lithium aluminum hydride. I'm going to draw it like this. So the first step is that the hydride is going to come in like so. So now we have H2O minus, and we added our hydrogen. Now lithium aluminum hydride, basically basic conditions, and we have an O minus. We see that we don't have an oxygen atom in our product. So how do we get rid of it? How can we get the O to just fall off? Well, recall that we still have this. And what happens is that the oxygen atom is going to coordinate with that aluminum complex. So you get something that looks like this. Like that. We've already added our hydrogen. So now what's happening here is we kind of made this oxygen atom a good leaving group now because it's coordinating with the aluminum. And now if we take a second equivalent of the lithium aluminum hydride, it can now, before we get to there, we want well, mechanistically, what we can do actually is take the lone pair on this guy and bring it down and kick that guy off. So what did we just generate here? Just like that. So what we've formed right here is called the aminium ion. So the aminium ion is now formed. So we can now take let's go down this way here. We can take a second equivalent of the lithium aluminum hydride, like so. And now we can use that to add another electron or another hydrogen, like so. When we do that, what do we generate? NH2. That hydrogen was already there. We just added another one. And there it is, completely reduced. Okay. Let me take a moment to look something over. So let's just clarify this piece right here, because it's the aluminum's negatively charged here. But note that it's lithium aluminum hydride, so you have the counter ion right next to it. And so we have the negative charge still on aluminum, but you have the lithium right next to it as well. And so that's what the species looks like. But the main part, you don't need to worry too much about that, as long as you understand that, hey, we go from the aminium ion to our amine. And we need at least 2 equivalents of the lithium aluminum hydride to make that transformation happen. Now what we're going to focus our attention on is nitriles. And we're first going to start off, how do we make nitriles? And you can do that if you take a alkyl halide, and this alkyl halide has to be primary or secondary. And if you just treat it with sodium cyanide, that's an ionic compound, right? So that it looks like this. we can see that we can do a SN2 reaction in which we can take that and go SN2 style to form our nitrile. Just like that. But there's another way that we can do this, and that is if you take an amide. If you take an amide and treat it with thionyl chloride, like that, okay, you will generate a nitrile. Just like that. You'll generate sulfur dioxide gas, which bubbles away, and then you get 2 moles of hydrochloric acid. So let's look at the mechanism with the time that we have left on how that process happens. Okay? So we'll see how much spore space we have and where we end up with. Okay? So here's our amide. And what does thionyl chloride look like here? SO, so that looks like this. Just like that. Okay. So what's going to happen first is the lone pair on the oxygen is going to come in and attack the sulfur atom and go like this. Okay. So that's going to bring us to this. And what else do we have here? Should still have a double bond there, like that, right? Just like that. But then we could see a resonance structure where this looks like that. H2, so that's positively charged. It looks like that. Okay. Now what can happen here? We have 3 lone pairs on that oxygen atom, so that could come down and kick off a chlorine. H2 plus okay, so what's our end goal here mechanistically? We want to get rid of the oxygen because it's no longer there, and we've got to get rid of these 2 hydrogens on that nitrogen atom. So we can take our base, and do we have a base hanging out around here? That could act as a base. So what we could expand out one of these hydrogens here, and we could envision that the chloride here can come and abstract that proton, giving its lone pairs. Now I'm going to erase these things right here. Okay. So we can keep going up the side here. So what does that do for us? Like that. O. Thionyl chloride. Okay, and then what did we generate up here? Plus HCl. that chlorine attacking there to forming the hydrochloric acid. Okay, so now we're here. Now what? So we need to get rid of one more of those hydrogens. And so when you're doing this reaction, you're going to have you're going to have additional chloride ions floating around as well. So what we're doing is trying to find a base, and I know that there's going to be some excess chlorides around. So what that's going to do is a second one is going to come and grab that proton, bring its electrons like that, and then kick that guy off. And when you take a look at that whole mechanism, it goes right there to the product. Let's double check one thing. So that goes to the product, but then what do we have left over here? We would have a O- connected to a sulfur, double bonded to a chlorine. And then the lone pairs on this guy can come back down and then kick that guy off. And what does that generate? That generates the sulfur dioxide gas. So that is how we can prepare nitriles from amides. It's a little complicated mechanism, but it's doable. Okay, that's where we'll end for today.